Hello dear student. In previous class, I discussed about the difference between orbit and orbitals. These are the difference between orbit and orbital. Next, I have also completed the Paul's exclusion principle. According to Paul's exclusion principle, no two electron in an atom can have the same value for all four quantum numbers. Then I have given also an example to explain the Paul's exclusion principle. Then I have also completed the conclusion of Paul's exclusion principle. Next, I have give also an important point why this principle is called Paul's exclusion principle, because the probability of accommodating more than two electron in an orbit is excluded. That's why this principle is called Paul's exclusion principle. Next, I have also completed about the above principle. According to the above principle, the electrons are filled in the various orbital of an atom in the increasing order of their energy. That is, orbital which having lower energy are filled first, then the higher energy leveled orbital will fill. It have two rule. According to the rule one, the orbital which having higher n plus L value having higher energy and it will fail later. That means the orbital which having lower n plus L value having low energy and it fail fast. The second rule says that if two orbital have the same n plus L value, then the orbital with a lower value of n has the lower energy and given examples. Then this is the important diagram. Now in this class I will explain about the Hund's rule. What is Hund's rule? For the electronic configuration, generally we follow this diagrammatical representation. By following this diagram, we can able to draw the electronic configuration of an atom or ion in terms of subcell. But suppose someone wants to draw the electronic configuration in terms of the orbital, then how will I draw the electronic configuration of an atom in terms of orbital? Let me show that. Before going to this topic, I will give a daily life example. Suppose I have three students. One is your X student, another is your Y student, another is your Z student. Suppose I have four chocolate. Suppose I have four chocolate. Clear? I want to give to the student. Each student belongs to the same class. They belongs to the plus two first year class. They belongs to the plus two first year class. Each having the same right upon me. So each have gained the same amount of chocolate. So what I will do? I have four chocolate. My first target, at least my first target is give one chocolate to each student. Yes or no? Are you getting my point? I have four chocolate. I have three students belongs to one particular class, that is your plus two first year. Every student have the same right upon me, so every student have a right to get a equal chocolate. But I have four chocolate. Then what I will do? That every child should get one chocolate. So I will to the Y. Third chocolate is to the Z. Again, remain one chocolate. Totally, I have four chocolate. Among from the four chocolate, I will give three chocolate to three student. Main chocolate will give whom? Since same right, you will give to any student after giving one chocolate, because the chocolate have your right to give anyone, because they have the same right. But to maintain an mm, and it is better to give the first student near to you. So I will give the chocolate to the X. The second chocolate will given to the X. If someone wants to give the chocolate to the Y instead of X, then it is also correct. If someone wants to try to give the chocolate to the Z instead of XY, then it is also correct. Suppose I have a 5 chocolate. Suppose I have 5 chocolate, 3 student. Then what I will do? I will give my first target. Give one chocolate to each student. Let me explain. Here I will give first chocolate to the X, second chocolate to the Y, third chocolate is the Z. Next remain 2 electron. So I will give to any two student. So here suppose I want to give X, then I can give Y. Next suppose I have 6 chocolate. Then how will I will distribute at first give one chocolate to each student because each have same right. They belong to the same class. Then the remain then the remain 3 chocolate will give again to each student. Give again one. That means is it. In this case, equal chocolate that is your two. Similarly, you can think about 5 student. Suppose 5 student that is your P Q R S. P Q R S. Suppose one is your another is your T. I have one chocolate. Then how I will distribute? Since five these 5 students have the same right because they belong to the plus two first year. So as per my choice, I will give to anyone. I will give to the or I will give to the Q, or I will give to the R or S or T. As your choice, you will give anyone because all the 5 have the same right. Suppose I have two chocolate. You will give one chocolate to P, another chocolate is your Q, or someone if you want to try give to R, another chocolate to the S. This is also correct. If someone try to give one chocolate to S, another chocolate to the T, it is also correct. But to maintain a uniform and a regular trend, it is compulsory to give. It is very necessary to give the chocolate from the initial to the last. Here the initial is your P, so first give one, then so first give one chocolate to P, second chocolate to Q, third chocolate is R. But here only two chocolate are present. Suppose I have 3 chocolate, then I will give one chocolate P, then Q, then R. Suppose 4 chocolate, give first S, then T. If 5 chocolate will present, similarly I have 6 chocolate. Give one chocolate to each. Then the sixth number chocolate is come to the P. Next, suppose I have 7 chocolate. Each getting 5 chocolate. Five orbital. 5 student get 5 chocolate. Sixth number chocolate go to the P. Seventh number chocolate go to the Q. This is the actual distribution in our daily life. Whether you think about chocolate or biscuit or notebook or any type, your target to maintain the uniformity. Otherwise, there will be a challenge for you to get the stability. If someone will give, suppose I have 3 chocolate, I cannot give the chocolate 2 chocolate to the P, 1 chocolate to the Q, and remain are empty. No, it cannot be possible. At first give one to each. After remain, you will distribute again. But everyone should get at least one chocolate. If you will have more chocolate, then you will again distribute. Like this daily life example, the electrons are distributed in the orbital. Remember, if you think about the subcell, every subcell have a different energy. So here there is no problem. It follow the above principle, and you will fill the electron from the subcell which is having low energy. But if you think about the orbital, look at that. Suppose I will think about the nitrogen atom. I will think about the nitrogen atom. A nitrogen atom having 7 electron. Nitrogen atom having 7 electron. Let me explain how I will distribute the chocolate electron. For the above from the above principle, I can say that here n is equal to 1, 1s, n is equal to 2, 2s, 2p, n is equal to 3, that is your 3s, 3p, 3d, n is equal to 4, that is your 4s, 4p, 4d, n is equal to 5, that is your 5s, 5p, 5d, n is equal to 6, 6s, 6p, 6d, sorry, here 4d, here also 4f, here also 5f, here also 6f. If n is equal to 7, then I can write 7s, 7p, 7d, 7f. You can think about the other orbitals. You can draw like this: first arrow mark, second arrow mark, third arrow mark, fourth arrow mark. This is your fifth arrow mark. This is your sixth arrow mark. This is your seventh arrow mark. This is your eighth arrow mark, nine arrow mark, 10 arrow mark. Yes or no? If you want to think about the nitrogen atom having 7 electron, atomic number is just 7. How I will distribute the electron in the subcell? Nitrogen atom having 7 electron. At first, your target to give electron to the 1s orbital, because why? Why I will give the electron to the 1s first? Because it have the lowest energy. So the first orbit is the first subcell is your 1s. Clear? Here we know that S subcell having 2 electron, P subcell having maximum 6 electron. It cannot carry 7 electron. D subcell having 10 electron, F subcell having 14 electron. Uh, among this is the highest value of each subcell. S having 2, P having 6, D having 10, F having 14. After that, they will not. The subcell have no capacity to gain this extra electron. It have maximum. Each subcell having a maximum number of electron. After that, it cannot receive the electron. No doubt, it have lower than the lower than the standard value, but it cannot exceed the value highest. It cannot exceed the more value than the standard value. That means S orbital have maximum 2. It may be 1 electron or may not be 1 0 electron, but it cannot have 3 electron. You cannot cross the maximum value. You can have low electron value, low number of electrons, but you cannot exceed the value these values. So I have a 7 electron. My first target is give 2 electron to the 1s orbital. Remember how I will represent the here I can write 1s, 2 electron is written in the right top side of the symbol of the subcell. That means you can write like this: 1s power 2. After giving 2 electron to the 1s, then the remaining electron is your 5. Now I will give the 5 electron to the other orbital. Which orbital will take the electron after 1s? That is your, this is your first row. Next, give to the second row. In the second row, 2s here present. So next target to give to the 2s. 2s having also maximum capacity of electron is your 2. So I will give 2 electron to 2s. After giving 2 electron to 2s, the remaining electron is your 3. So go to the next subcell. Here I will go to the third arrow. In the third arrow, 2p will come. Now P having maximum 6 electron. But here the remaining electron is your 3. So give 3 electron to the 2p3. This is the electronic configuration of nitrogen atom in terms of subcell. Suppose I want to give the electron of orbital. Then how I will draw? 1s subcell having one orbital, that is your 1s. It will also present in the 1s. Two electron present in the 1s. It have it have one orbital, so no problem. 2s having also one orbital, that is your 2s. Again give 2s square. Next, if you think about the 2p. 2p having 3 orbital. 2px, 2py, 2pz. Then how I will distribute the electron? Here is the problem. To solve such type of problem, we generally follow Hund's rule. Hund's rule tell us if the orbital having the same energy, then every orbital at least gain one electron. After gaining one electron, you can give two electron to the you can give the second electron to the orbital. Otherwise, you will not give. Every orbital have a right. At first, they gain one electron. Then they will think about the second electron. So, what is the statement of Hund's rule? Go to the statement of Hund's rule. Pairing. Pairing means two electron. Each orbital having maximum pairing. That is just said to be pairing of electrons. Pairing of electron in the orbital having the same or nearly same energy. Think about the orbital of a particular subcell px, py, pj. Don't think about dxy and px. No, these are two orbitals are different subcell and they have also different energy. You can think about px, py, pz simultaneously. You can think about the d orbitals, that is your dxy, dyz, dzx, d x square minus y square, dz square. You can think about this because these five orbital having the same energy, nearly same energy or same energy. These three orbital having nearly same energy or same energy. So, pairing of electron in the orbital having the same or nearly same energy. If an orbital having the same energy, that is it. That is termed as the degenerate orbital. Degenerate orbital means having same energy or nearly same energy. The orbitals which having same energy, that is called degenerate orbital. Your px, pyz are 3 are said to be degenerate orbital. But you cannot say that dxy and px are said to be degenerate orbital energy. Because dx belongs to d subcell, px belongs to p subcell. So, pairing of electron in the orbital having same or nearly same energy will not take place until each orbital is single filled. Single field means each orbital must gain one electron. Then you will give the second electron to the orbitals. So pairing does not start until each orbital will take a single electrons. This is the statement of Hund's law. Let me explain the electronic configuration. Here I have given the nitrogen atom. Nitrogen atom 7 electron. If you think about the electron configuration in terms of subcell, here I can write 1s2, 2s2, 2p3. If you think about the orbital, then what I will do? I will write here 1s2, 2s2, then I will write 2px, 2py, 2pz. Our remaining electron is 2. At first give 2 electron to 1s, then another 2 electron 2s, then the remaining electron is 3. So according to the I can give 1. So the electronic configuration of nitrogen atom in terms of orbital is this. This is configuration in terms of orbital. I can write 1s to 2s 2px1, 2py1, 2pz1. Suppose think about the oxygen atom. Oxygen atom have 8 electron. So at first I want to draw the electron configuration in terms of the subcell. At first give the electron to the 1s gain 2 electron. After giving 2 electron, the remaining electron is your 6. 8 minus 2 means 6. Next give the electron to the next orbital, that is 2s. So give 2 electron to the 2s. This is your full field. S orbital having capacity 2, so it is said to be full field. But if you think about px, 2px, it is half field, because px orbital having the capacity 2 electron, but it have 1 electron, that means half of the 2. So if an orbital completely filled, that is said to be full filled. If an orbital will gain half of the full fill, that is said to be half filled. So let me explain the electron configuration of oxygen. I can write 1s2, 2s2. After giving 2 electron to the 2s, then the remaining electron is your 4. Now come to the uh, mm, next orbital. Next orbital is your 2p. So here I can write 2p. P having 6 electron, but I have 4 electron. So give like this 2p 4. This is the electron configuration of oxygen in terms of subcell. Suppose I want to draw the electron configuration in terms of orbital. I can write here 1s2. Next, here I can write 2s2. Next, if I will think about the 2p, then here I can write 2px, 2py, 2pz. Give one electron to each. Fifth number electron goes to the 2px. Sixth number electron go to the 2py. Seventh number electron goes to the 2pz. After giving 3 electron, then the remaining electron is your 1. Now your choice, you give to anyone. You can give to px, you can give to py, to pz, as your choice, because both because all the three have the same energy. So here I want to go to the first, that is your 2px2. So the electron configuration of oxygen is your what? 1s2, 2s2, 2px2, 2py1, 2pz1. Look at that. Here 1s orbital having capacity 2 electron. This is your said to be fulfilled. 2s orbital having capacity maximum 2 electron. This is filled. So this is your said to be fulfilled. 2px having capacity 2 electron. It have also 2 electrons. So this orbital is said to be fulfilled. But if you think about the 2py, 2pz, it each having 1 electron, that means half of the 2 electron. So this is your said to be half filled. This is your said to be also half filled. Clear? This is your Hund's rule. Let me explain the electron configuration of other atom. Then how I will write. Let me explain. Suppose come to the first electron. The first atom, that is your hydrogen. Hydrogen having 1 electron. So here I can write 1s1. Next give to the helium. Helium having 2 electron. Gives 1s2. Clear? Hydrogen helium. Next go to the lithium. It having 3 electrons. So first give the electron to the 1s. Let me explain. So here I can write 1s2, 2s1. Next you will write this is your lithium. Next you can write 1s2, 2s2. Next beryllium, boron. That is your atomic number is a 5. I can write 1s2, 2s2, 2p1. Clear? Again I want to draw the same diagram. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7s, 7p, 7d, 7f. You can give the arrow mark like this. Clear? Now come to the next atom. After boron, the next atom is your carbon. How I can write this is your carbon 6. Go to 1s2. First give 1s2. Next is your 2s. Give 2s2. 2 plus 2 that is your 4. Give 2p2. If you want to draw the electron configuration in terms of orbital, then I can write 1s2, 2s2, 2px, 2py, 2pz. Give 1, 1. 2pz is your 0. You cannot try. You as your choice. You will write or not. This is the atomic electron configuration of carbon. Let me explain another atoms. Look at the another atoms. Here I have given. Think about the nitrogen atom. I want to try to solve here. Nitrogen having atomic number already I discussed, so it is not necessary to give nitrogen and oxygen. Move to the fluorine. Fluorine having atomic number 9. So the electron configuration is your 1s2. Next is your 2s2. Next is your 2p5. 2 plus 2 plus 5 is your that is your 9. Next come to the neon. Neon having 10 electron. Let me explain clearly. Give some time. Okay. Okay, think about the fluorine. Come to the fluorine. Here I will give the electron first to 1s. Already I have given 1s. Next I will give 2s. Already given 2s. Next go to the 2p. Okay, next here 2p, 2p, 5. P electron, but it have 5 electrons, so you can write like this. But if someone wants to write the electron configuration in the terms of orbital, then how you will write? Look at that. You can also draw the electron configuration in terms of box. Here one box, two electron, one is your clockwise, another is your anti-clockwise. Here two is having two electrons, so here I can write like this. One is your clockwise, another is your anti-clockwise. Similar thing about 2p, 3 orbital is present here. 2px, 2py, 2pz. I have drawn the diagram like this. At first I will give one electron to each. Then after giving 3 electron, the remaining electron is your 2. So I will distribute the electron from the initial second electron. This is the second electron. We know that every orbital having two electron, maximum two electron, and the two electron are spin in opposite direction to each other. You can write the electron configuration in such way: 1s2, 2s2, 2px1, 2px2, 2py2, 2pz1. You can write like this. You follow this such type of structure when you will think about the hybridization in the upcoming class. In the chemical bonding chapter I will give you about the give you details about the hybridization. For that you can write such type of structure, but simply you can write 1s to 2s to 2p5, or you can write the electron configuration in terms of orbitals. Next is your next element is your who is the next element? Neon. Neon having 10 electron. Look at that, 1s2, 2s2, 2p6. Okay, 2 plus 2 plus 6 is your 4. You can draw the like this, 2 electron, here 2 electron, 2s, 2 electron. 2p, 6 electron, 1, 2, 1, 2, 3, 4, 5, 6. You can also write the electron configuration in terms of like this. For neon, 1s2, 2s2, 2px, 2py, 2pz, give 1 electron, 1, 1. I have 10 electron plus 2, 4, 5, 6, 7. Again gives 1 electron extra, 1 electron, here 2, here 2. So the electron configuration is your 1s2, 2s2, 2px2, 2py2, 2pz2. Similarly, follow the diagram, then you can able to write the electronic configuration. Suppose if I want to think about draw to the electron configuration of an atom, that is your suppose scandium. If I want to draw the electron configuration of scandium, then what I will write? Scandium having the atomic number is 21. That means it have 20 electron. Scandium having 20 electron. Yes or no? So first electron goes to which orbital? That is your 1s. So here I have given 1 electron to the 1s. 1s2. 2 electron reduce, that means in total 9 electron. Next electron give to the 2s. 2s here will come. Again remove 2 electron, that is your 17 electron. Give 6 electron to the 2p. 6 electron. 6. Here I can write 11. Next give to the electron the 3s. 3s2. Give 2 electron, that means 9. Next give to the 3p. 3p. 6 electron. Remove 9 minus 6, 3 electron, remain 3 electron. Next give to the 4s. 4s2. Clear? And next remaining electron is your 1. After 4s3 come to the 3d. This is your 3d1. Similarly, think about the, you can draw the structure like this in terms of orbital. Then you can draw scandium. After scandium, the electron is your titanium. Draw the diagram. Same style. 1s2, 2s2, 2p6. You can move the whole structure. Now come to the structure. You can draw the structure like this. 3p 6 4s2 3d2. Next after scandium titanium, next is your vanadium. 1s2 2p6. You follow the diagram and draw the electron number. 4s2, next 3d3. After scandium titanium vanadium, next is your chromium. Later I will explain the chromium. Next give to the manganese. Chromium remain. Next go to the manganese. Manganese have the electron configuration is what? Look at that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Go to the, I have given thing, I will draw later about the chromium. Next thing about iron 26, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Next go to the cobalt 1s2, that is your 27, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Next go to the nickel 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. No, exclude the copper. Later, I will explain. Think about the zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Next go to the nickel 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Remove 9 minus 6, 3 electron, remain 3 electron. Next go to the copper. Later I will explain. Think about the zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay. Find the electron configuration of the atom from 1 to 30. I have I have not carried out two example. One is your chromium, another is your copper. Let me explain. Remember an important concept. Remember an important concept. Suppose an orbital having suppose an orbital which any type of orbital. Suppose an orbital having one electron. Orbital having maximum how much? Two electron. Suppose an orbital having one electron. Then the orbital is said to be half filled. Then the orbital is said to be half filled because half of the full filled means two. If an orbital having one, if an orbital have two electron, that is just said to be full filled. Remember, if an orbital is completely filled, then it is more stable. And the orbital which having half filled, that is your. If an orbital having zero electron, that is just said to be unstable. Clear? Remember this. You can take any type of orbital px, py, pz, dxy, dyz, dzx. You can take any orbital. If the orbital have one electron, that is said to be half filled. If the orbital having two electron, that is just said to be full filled. Full orbital is more stable as compared to the half fill, as compared to the unstable which having zero electron. So remember this point. Similarly, if you think about the S subcell, if an S subcell have maximum two electron, subcell having if an S subcell having one electron, that is your half fill. If S subcell having two electron, that is your full fill. Think about the P subcell. P having maximum 6. If it have a complete fill, that is a maximum 6, that is said to be full fill. If a P having 3 electron, that is said to be half fill. Clear? Similarly, think about D. D having 10. If T have 10, that is said to be full fill. If D have 5, that is said to be half fill. Similarly, think about F. If a F have electron, that is your full fill. If F have 5 electron, that is your said to be half fill. Remember an important point: fulfill. Fulfill whether orbital or subcell. You can take any. Fulfill subcell or orbital is higher stable. This is the stability order. Remember this stability. Fulfill orbital having more stable than half fill, then unfair, that is your not half fill, not fulfill. Clear? That is your not half fill, not fulfill. Not half fill, not fulfill. Are you getting my point? Let me explain. If you think about the 1s1, here s orbital is present, it have one electron. So tell me, it is a half filled or full filled? It is said to be half filled because it have maximum two electron, but it have only single electron. So it is said to be half filled. Next thing about let me explain. This is your less stable. If an orbital having full fill, then it is most stable. If an orbital half fill, then it is less stable as compared to the full fill. If an orbital do not have any electron, that is just said to be unstable. So here we can think about less stable, but here there is a stability. Think about 1s2. S orbital having 2 electron maximum, it completely 2 electrons, so this is just said to be fulfilled. This is just said to be fulfilled. Lithium. This is your what? fulfill. This is also fulfill. Yeah, lithium you can write 2s1, not 2s2. Clear? This is wrong. You can write the electron configuration in this way also. Look at that. Here we can write the inert gas. In the upcoming class, you will clearly explain, or you will clearly understood about how can you write this. But for this class, stop here. Don't think about this. Next thing about beryllium, one has to fulfill. Here also this is fulfill. For lithium, this is your fulfill. This is your half filled. Next thing about boron. Boron having fulfill, one has fulfill, two has fulfill, but this is not fulfill or not half fill. Because your p orbital is present, if p orbital 3 electron, that is your half fill. If p orbital having 6 electron, that is your fulfill. So this is not half. Are you getting my point? Next thing about the carbon. Carbon your fulfill. This is your not half fill, not fulfill. If you compare the stability, your 1s 2s having more stable than the 2p. Because 1s 2s belongs to the fulfill, 2p is not belongs to half fill or not half fill or not fulfill. Nitrogen, one fulfill. This is your half fill. The stability goes on increases after carbon to nitrogen. Next, oxygen, fulfill. This is your not half fill, not fulfill. This is your stable. This is your stable, but this is not stable. This is unstable. Similarly, think about you can detect any orbital whether it is half fill or full fill or not, or you can think about may not half fill, may not be full fill. You can detect by drawing the electron configuration and see the number of electron present in the subcell or orbital like this. Let comes to the copper. Let comes to the that is your chromium, that is your 24, and copper. The recently I have given a suggestion that is your fulfill is more stable, half fill less stable but stable, not half fill, not fulfill. That is your unstable. You can think about unstable. Suppose I want to draw the electron configuration of chromium. Then what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, that is your 3p6. Next, after 3p6, you will come to the 4s. This is a 3, that is your 3d4. Clear? At first, I want to think about the chromium. Here, this is your full fill, this is your half fill, this is your this is your fulfill, this is your fulfill, this is your fulfill, but it is not half fill, not fulfill, not half fill, not fulfill. Look at that. If you think about the chromium, except 3D, all orbitals are stable. Suppose 3D will stable, then all the orbitals will stable, and finally chromium atom will stable. Only due to the 3D orbital, totally you can think about the unstable. You think about the unstable. No doubt all orbital are stable, but since 3D is unstable, so the chromium atom is, you can think about the unstable. You can detect the stability of the chromium. Now, look at that. These three orbital is unstable due to lack of one electron. If it gain one electron from any from other, then it complete the half fill. At least it added in the stability list. It will added in the stability list. Due to lack of one electron, the total the orbital atom is unstable. If all the orbitals are stable, then the atom is stable. In chromium, all are stable except 3D. Suppose someone give an electron to the 3D, then it becomes 3D5. It will attain the stability list. It keep his name in the stability list. Yes or no? Then who will give the electron to 3D? The total electron is 24. It is correct. It is if you change the total number of electrons, then it will give to represent another atom. Actually, chromium have 3D 4 electron. 3D have 4 electron. But if you will give one electron to the 3D, it will convert 3D5 and it maintain the half filled configuration and it will added in the stability list. Then a question will arise: who will give the electron to the 3D? The source who is source will give to the one electron to the 3D. Here an electron will go to the 3D. Suppose think about an orbital. This is suppose an x orbital. One electron shift to the 3D. Then 3D comes to 3D5 and it will stable and whole atom will stable because other rest atoms are already stable. Rest orbitals are already stable due to fulfill. Which type of orbital will donate one electron to 3D? The orbital which having nearly same energy with 3D. Nearly same energy or same energy with 3D. X if X will donate one electron to 3D, then X must follow some condition. X must have equal energy with 3D. Yes or no? After giving one electron to the 3D, it must stable. If X will give one electron, after giving one electron, the X must be stable. Otherwise, it will not be stable. Remember, very important point. Such orbital will give the electron to 3D which having the same energy with 3D. And after giving the electron, the donating orbital must be stable. Otherwise, it is not allowed to give electron to the 3D. Look at that. 1s stable, 2s stable, 2p stable, 3s stable, 3p6 stable, 4s stable due to fulfill, 3d is unstable. Suppose think about 4s. If we will check the electron of 4s, sorry, energy of 4s and 3d, they are nearly same to each other. So among the different orbital, only 4s orbital is selected for donating one electron to the 3D and 3D and the 3D orbital will attain the half fill configuration and it will listed in the stability column. As a result, it will stable and whole atom will be stable. So what happens here? If you will check the criteria of 4s, 4s having same energy with 3D, nearly same energy with 3D. If 4s shift one electron to 3D, 3D will 3D5, here 4s1. Now look at that. After removing one electron from 4s2, after removing one electron from 4s2, it will changes 4s1. Look at that. This is your fulfill. This is your what? Half fill. It is stable. It is more stable. It is less stable, but it included in the stability list. Look at that. As per the rule, as per the rule, it is compulsory to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 4. But to maintain the stability, one electron is shifted from 4s to 3d. No doubt, after giving one electron to 3d, its stability decreases, but it cannot unlisted. But it cannot listed in the unlisted list. It listed in the unstability list. It remain in the stability list. No doubt there is a decrease in the stability due to half fill conversion of a fulfill to half fill, but still the orbital is stable. So here what happened? One electron is shifted to the 4s from 4s to 3d, and you can write like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Look at that. If I want to shift one electron from 4s to 3d, then this is the structure. Look at that. Here fulfill stable, here stable, 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 stable. It is half filled. It is also listed in the stability order. No, look at that. It is also stable, so it is listed in the stability order. Okay. Such type of transfer of one electron from one orbital to another orbital will possible in two conditions. The two orbital must have the nearly same energy. They are near to each other. After giving the electron, this orbital must be stable. Look at that. After giving one electron 4s2, it gives it converted 4s1. 4s2 stable, 4s1 is also stable, but it have slightly less stable as compared to 4s2. But it cannot listed in the unstability orbital list. So the corrected electron configuration of copper is what? 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. You cannot write like this. This is due to increase the stability. Increase the stability. If you think about the copper have 29. Here you can write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That is your 3d. Yes, 3d9. Same style. Here 3D wants an half filled orbital, here 3D wants a fulfilled orbital. No doubt it have a more electron as compared to the half filled, but it is said to be unstable. So in this case, what will happen? One electron is shifted from 4s to 3d to increase the stability. So the actual electron configuration is your 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. This is the correct electronic configuration. Remember, such type of case will happen in which two orbital having same energy, and after donating the electron, the donated orbital must be stable. Look at see the electron configuration of the atoms. All the atoms obey the above principle, Hund's rule. But if you think about the chromium and zinc, they just divert the last orbital to attain the stability. So look at that. Vanadium last is a 3d3. Chromium actually 3d4, but to maintain stability, here I can write 3d5. Manganese and chromium having both having 3d5. Next, give iron 3d6, cobalt 3d7, nickel 3d8. But if you think about copper, actually it was 3d9, but it is changed into 3d10. Automatically, zinc have also 3d10. This is the electronic configuration of an atom. Look at that. You can draw the electron configuration in various way. Later, I will teach you how can you draw the electron configuration of such type. It is also an short type short concise electronic configuration. It is a short electron configuration. If you will draw the electron configuration, then it will take vast area. Vast, it is a very difficult. It need more space. But if you need concise, then you will draw the concise electron configuration like this. Look at that. How you? I will give some hints about to this. See, sodium have the electron configuration. This is the electronic configuration of sodium. If you think about the sodium just nearer to the neon. Neon is the noble gas. Noble elements are those elements which having the stable electronic configuration. Stable electron configuration means in the valence cell it must be a complete cell. That means it may be follow the octet or duplet rule. So sodium have exactly electron configuration 1s2, 2s2, 2p6, 3s1. But if you want to write the electron configuration in short manner, look at that. Write the nearest noble gas. Noble gas means noble elements means the element which obey octet or duplet. Look at that, neon having completely filled electron. All the orbitals are filled with their maximum capacity. So I have written neon 10. This is your neon 10. Yes or no? Same, neon 10. Clear? Here neon 10 is given. 10 means atomic number. So this is the inert gas. Then the rest is your 3s1. Similarly, think about magnesium. This is your neon. This is your neon. So I have written neon 10 and the rest is your 3s2. You can convert this electron configuration into the nearest noble element. That means which obey the octet or duplet rule. Later, I will explain clearly about such type of electronic configuration. For today class, only just remember there is another form to write. There is another way to write the electronic configuration by using the noble elements. Noble gas. That is your helium, neon, argon, krypton, general like this. Let comes to the electron configuration. Let me explain a question. Fulfill having more stable. Full half fill having less stable. If an orbital or subcell having no fulfill, no half fill, no half fill, no fulfill, that is said to be unstable. Then there is a question. A question will come to your mind. Why fulfill orbital or subcell are taken as stable, more stable? Why half-filled orbital is less stable as compared to the full-filled? A question must arise in your mind. This is due to, remember, this is due to the symmetrical arrangement and larger exchange energy. Only remember these two words, symmetrical energy and larger exchange energy. The half field and full field get the extra stability as compared to the other subcell or orbital. So here I can write the extra stability of half field and completely filled electron configuration is due to their number one symmetrical arrangement, number two large exchange energy. Let me explain the electron configuration of an ion. Electronic electronic configuration of an ion. There are two type of ion. One is your positive ion, another is your negative ion. Remember an important point. Suppose this is your nucleus, this is your K cell electron, this is your L cell electron, this is your M cell, this is your N cell. Always remember an important point. The electron present near to the nucleus is more stable. More stable and it have, try to understand, it have less energy but more stable. Stability and energy always inversely proportional to each other. If a species having more energy, that means this is more unstable. Stability and energy. If an species having more energy, it having less stable. Less energy, more stable. So the electron nearer to the nucleus are always more stable and having less energy. The cells which are away from the nucleus, they having more unstable and more less stable but more energy. Remember also important point. Suppose you want to give an electron to an atom. Suppose you will take an X atom and one electron suppose you will give to the X atom. Then a question must arise in your mind. The electron goes to which cell or which subcell or what may be. We think about cell. The electron will go which cell and it will stabilize. Remember important point. If you want to give an electron to an atom, then the atom always keep the electron in the core cell, not the valency cell. Because valency cell are unstable as compared to the core cell. So when you want to give an electron to an atom, the electron take the electron and it will keep the electron in the inner cell, not outer cell. So add electron in the core cell. If you want to remove an electron from an atom, suppose this is your X atom, I want to remove an electron from the X atom. These are K cell, L cell, M cell, N cell. This K cell is more stable. Yes or no? This is your more unstable. Tell me, from which cell you will remove an electron? If you will remove an N cell, then it is very easy because it is highly unstable. The electrons are also unstable. So the electron removal from N cell is easy because N cell is said to be the valency cell. But if you think about remove an electron from M cell, then it is very difficult as compared to the N cell. Because M cell is nearer to the nucleus as compared to the N cell, so its stability is more, it have a less energy. Similarly, think about L cell and K cell. Then it is again more very difficult because they are under control of the nucleus effectively. So remember an important point. If you want to add electron, then go to the core cell, that is your inner cell. If you want to remove an electron from an atom, then go to the valency cell. Then it is very easy to maintain the stability. Always remember, if you want to give an electron to an atom, then the electron will go to the core cell. If you want to remove an electron, then the electron will remove from the valency cell. Clear? Let me explain the electronic configuration of ion. We are talking about the first ion is suppose O2 minus. Before going to electronic configuration of any ion, whether it is a positive or negative, at first draw the normal atom. Here the normal atom is your oxygen. That is your 8. Here we can write 1s2, 2s2, 2p, how much? 2p, 4. Here we can write 2px2, 2py1, 2pz1. Clear? 1s2, 2s2, 2px2, 2py1, 2pz1. You know that when oxygen atom release 2 electron, then it convert sorry. When oxygen atom gain 2 electron, then it converted into O2 minus. Let me explain. Here oxygen had 8 electron. Now the number of electron in the oxygen atom is your how much? That is your 10. Clear? Because oxygen initially it have 8 electrons. When you will give 2 electron, then the total electron is your how much? 10. Yes or no? So that two extra 2 electron go to the which cell? It must go to the core cell, not valence cell. Otherwise, it will not go to the valence cell. Look at that. Here 1s2 is completely filled, 2s2 filled, 2p x2 filled, then the 2 electron go to the 2py, 1 electron to the 2py, another electron the 2pz. This is the electron configuration of O2 minus. Again, I want to write oxygen. So your target to write the electron configuration of O2 minus. Always remember, if you before going to write the electron configuration of an ion, you will think about the electron configuration of the atom. Clear? Again, I want to write oxygen having electron configuration 1s2, 2s2, 2px2, 2py2, 2pz. Sorry. 2px2, 2py1, 2pz1. Clear? This is the electron configuration of oxygen. Two electron you will add. You will add the electron from the core cell. If all the core cell will fill already filled, then you think about the valency cell. Look at that. Here one is now. Let me explain. It have 10 electron. One is two, two is two, like the atom same. Next 2px, 2py, 2pz. Your 2 is present, your that is your 1 is present, your 1 is present. Again, you have remain 2 electron. So give this electron, this electron. You cannot enter into the core cell because core cell already filled. You cannot give that. So in this case, the core cell are filled. So come to the valency cell or next cell which are empty. Suppose think about another negative charge, that is your Cl minus. Before going to the Cl minus electron configuration, about Cl. That is you are having 17, 1s2, 2s2, 2p6, 3s2, how much? 2 plus 2 plus 6 plus, that is your 12. Remaining your 5. So here I can write 3p 5. Yes or no? Is this the chlorine? You can verify 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Verify this. Clear? 1s2, 2s2, 2p6, 3s2, 3p6, 3p5. Okay? Look at that. Suppose I want to form Cl minus. An extra electron is given to the Cl. Then it will convert it into Cl minus. Otherwise, it will not have. It will not form. So Now the total electron in Cl minus must be 18. Draw the electron. These are the core. These are the orbital present in the core cell. So write down first 1s2 filled, 2s2 filled, 2p6 filled, 3s2 filled, up to these 3s all are filled. Now all the core cells are completely filled. The valence cell that is 3. Your 3 having 3p5, 1 electron is remain. So the one electron is added into the 3p. So the electron configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p6. After gaining one electron, look at that. The 1s stable, this stable, this stable, stable, stable. All are stable, so Cl minus is stable. Clear? Think about a positive charge. Think about calcium, Ca2 plus. How you will draw. Think about Mg2 plus. How you will draw. Before going to the electron configuration of ion, think about the first atom. Calcium having atomic number is 20. That is your 1s2, 2s2, 2p6, 3s2. How much? 4, 3, 3p6, 3d. What? The 2 plus 2, 4, 10, 12, and that is your 18. Yes or no? Calcium. Here I already given calcium 3p6. Okay, 3d2. 3d2. 4s2. Yes, 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 yes. Wrong, wrong. That is your 4s2. Clear? This is the electronic configuration of what? Calcium. Think about Ca2 plus. Calcium when loses 2 electron that converted into Ca2 plus. So there is a removal of 2 electron from calcium. As a result, you will get the Ca2 plus. Electronic configuration of calcium is this. Now draw the electron configuration Ca2 plus. Remove 2 electron first. Always remove the electron from the valence shell. And if you want to add an electron, then go to the core cell. Here 1s belongs to K cell, 2s 2p belongs to L cell, 3s 3p belongs to M cell, and 4s belongs to N cell. So here N cell is the valency electron, so remove 2 electron from the 4s. So here you can write Ca2 plus having the structure like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s0. Clear? Or you can your choice, you will write or not. The electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Clear? Next, go to the copper. Copper, that is your CO. Think about the electron configuration. Here the electron configuration is this: 1s2, 2s2, 3p6, 4s1, 3d10. This is your 1s case, 2s2p L cell, 3s 3p 3d M cell, 4s is the N cell. So your valence cell is the 4 N cell belongs to, that is your 4s1. Your target to form the Cu plus. Cu having electron configuration is this. Yes or no? This is the electron configuration of Cu. Remove one electron from the 4s. So the electron configuration of copper is your how much? 1s2, 2, 2p6, 3s2, what? 3s2, 3p6, 4s0, 3d10. You can write 4s0 or not as your choice. But this is the electron configuration of Cu plus ion. Like these ion, you can also think about F minus ion, fluorine having 9 electron, but F minus having 10 electron. So look at that. If you think about the electron configuration of fluorine, 1s2, 2s2, 2p5. Here 2p6 is present, so one extra electron is added in the valence cell. Here no course, here the core cell is filled, so you cannot write here. Similarly, you think about the different ions, and you can draw the electronic configuration of each ion and atoms. This is all about this chapter. Finally, I completed this chapter. In the upcoming class, I will discuss about a new chapter. See, look at the new chapter. The new chapter is your what? Periodicity. In this class, I completed the structure, atomic structure. In the new chapter, I will start in the upcoming class. That is your classification of element and periodicity in property. This is the new chapter. I will start in the upcoming class. For this class, the course is completed. Thank you all watching the video continuously. At last, I would like to say that please subscribe the channel, click the bell icon. As a result, you will get a notification before the beginning of the class. Give a like to motivate me. Thank you again. Namaskar.